Welcome, everyone. This is Spintronic seminar number 74. Our speaker today is Dr. Shaloo Rakheja from the University of Illinois at Urbana-Champaign. She started as an assistant professor there in the electrical and computer engineering department in the end of 2019. Before that, from 2015 to 2019, she was an assistant professor in electrical and computer engineering at New York University. And prior to that, a postdoctoral associate at the Microsystems Technology Laboratories at MIT. She received her master's and PhD degrees in electrical and computer engineering from the Georgia Institute of Technology, respectively in 2009 and 2012. Shaloo's research interests are in understanding, predicting, and modeling physical phenomena in materials that drive their functional behavior and enable applications such as low-power logic and memory, sensing, and wireless communication. So the topic of Dr. Rakheja's talk today is modeling of chromium oxide, non-volatile, and secure memory and Terahertz oscillator. And with this, I'll give it to you, Shaloo. Please go ahead.
All right, thank you. So I want to especially thank the organizers for giving me the opportunity to talk to you all about my research in chromium oxide, non-volatile and secure memory, and Terahertz oscillator. And I think that this is very timely because last week we had Professor Christian Benek's talk in chromium oxide. And if you attended that talk, then you already know everything about magnetoelectric effect in chromium oxide, which makes my job very easy. So before I get started, I also want to thank our grant sponsors, the Semiconductor Research Corporation, the National Science Foundation, and the US Department of Energy for generously supporting my research over the last several years. So before let me see, this is not working. Okay, now it's working. Okay, before I get started, I just wanted to give you all a brief overview of my research. The focus of my lab is mainly theoretical. So we look into electronic and spintronic devices. We do their compact modeling, circuit modeling, as well as material modeling for a number of different kinds of applications related to low power logic, memory, as well as RF communication. And the kinds of materials that I worked on are listed in this box on the left-hand side. I've looked into 3, 5, and 3 nitrides and gallium oxide for high electron mobility transistors, as well as photoconductive switching, both for RF as well as high power electronics. And I'm hoping that very soon I'll be able to work on other ultra wide bandgap materials listed over here, which are these alpha indium aluminum gallium oxide diamond and hopefully aluminum rich nitrides. And we've also looked into spin charge coupling in topological insulators, 2D materials. But more recently, my work has focused on these antiferromagnets, nickel oxide, chromium oxide, which are these insulators. And my talk today focuses on chromium oxide. So we've also started looking a little bit into these manganese-based antiferromagnets. These are metallic in nature, coplanar, non-collinear antiferromagnets, and they have some interesting dynamics. But as I said, chromium oxide is something that we'll be covering in much great detail today. And this is a very specific kind of a material. It is magnetoelectric in nature. To kind of set the stage for my talk, I want to very quickly summarize the interest from the community in looking into antiferromagnetic spintronics. So antiferromagnets, as we all know, are materials in which the moments on the neighboring atoms are aligned in an anti-parallel fashion. So this is an example of a layered antiferromagnet where we can see antiferromagnetic coupling across these crystallographic planes and ferromagnetic coupling within the plane. But on the whole, there is a cancellation of the net magnetic moment. And in his 1970 Nobel lecture, Neil said that these were interesting materials, but probably they wouldn't have any use. So before getting into the useless part of it, let's see what are some of the interesting features of antiferromagnets. So the first thing is that they are robust against external magnetic field perturbations. And this is one of the reasons why my group started looking into the hardware security applications of these materials and whether or not we could realize some robust primitives for security on the chip, and hopefully have them in a CMOS compatible manner. They also do not have any stray magnetic fields. So then this would mean that they do not have this magnetic interference, and you could probably integrate them in dense networks. The dynamics are also ultra fast in the terahertz range. And finally, they display large magnetotransport effects. So essentially, the point is that antiferromagnets do not suffer from the specific weak points of ferromagnetic-based spintronics. But there are a number of issues, because if we have to use antiferromagnets as active elements for spintronics devices and applications, we really need to invest a lot more into understanding how to write this antiferromagnetic order. And then importantly, and very critically, we also have to read the variations in the antiferromagnetic order. So researchers have been working in this area. This has been a very, very intense active area of research, also evidenced by a number of review articles in Review of Modern Physics that have come up. So I've listed a few review articles at the bottom here. So I think one of the ways we can really make sure that antiferromagnets become key elements in future spintronics applications is by this sort of the joint effort in developing predictive models, disruptive materials, as well as looking into new experimental designs that can probe this. So with that, my research in Chromium was really inspired by these two inquiries. First, could we use these antiferromagnets as showstoppers for spintronics devices? But importantly, and I have to thank Christian for kind of involving me and engaging me in the research that they were performing as part of SRC project. We also wanted to look into specific kinds of antiferromagnets whose order could be fully electrically controlled. And this is important because we want to have energy efficiencies close to silicon and also make sure that these devices are CMOS compatible. So with that, we've been looking into this magnetoelectric antiferromagnet Chromium. And we've done two kinds of devices in this. The first is a passive non-volatile memory device. This is driven purely by the magnetoelectric mechanism. And in fact, I shouldn't say purely magnetoelectric driven mechanism, because I'm going to very briefly talk about our work with Christian in looking into the switching of boron-doped chromium. And then the second device we've looked into is a spin-torque-driven active device. So this is a terahertz oscillator, and it can also generate spikes. And there's been a number of papers now in antiferromagnetic oscillators coming out of prominent groups in Oakland, Professor Slavin's group, for example. And so we've looked into both of these. And our goal as electrical engineers was to take our understanding from materials and physics and enable some compact models and circuit models for switching kinetics, and also model the collective order dynamics. I cannot ever overemphasize the need for device and circuit models, because these are the models that basically take materials and then enable applications. And so we can do SPICE modeling, circuit modeling, and benchmarking of these devices. So with that, let's get started into the main part of the talk. So this is a unit cell of chromium containing 4 chromium ions. Its magnetic structure is well known from neutron diffraction measurements and magnetic susceptibility data, and its Néel temperature is about 307 Kelvin. But as Christian described last week, boron doping has been known to increase the Néel temperature of chromium to 400 Kelvin. Strain engineering is also useful in order to control the Néel temperature, because it depends very strongly on the exchange coupling constants. And a lot of theoretical work was also done by Kirill's group, actually, in predicting the enhancement of the Néel temperature by boron doping. In fact, I think when I first started looking into chromium, Kirill's papers were the only papers I was initially reading. And so I feel like I've known his work for a very long time. So anyway, below its Néel temperature, chromium develops this collinear spin ordering that I'm showing in the figure here. And the free energy density of chromium contains a term that is proportional to the product of the applied electric and magnetic fields. So this is the magnetoelectric effect. And the constant of proportionality here is the magnetoelectric susceptibility, which it's not a very high value. It's about 3 picosecond per meter, and it occurs at a temperature that's below the room temperature. But the nice thing about this magnetoelectric effect is that we can directly electrically control the antiferromagnetic domain state, as I'm showing in the figure here. So chromium does contain roughness and sensitive boundary magnetization that is coupled one-to-one with its bulk antiferromagnetic order. And we can then do a constant value of the magnetic field, a small one, can be applied, and then we can change the polarity of the electric field and switch the antiferromagnetic order and the boundary magnetization. And this can then be read either using an exchange bias setup or a ferromagnetic free setup, and so on. So this is very interesting. And starting from the 1960s, there has been a lot of work in understanding first the physics and then the kinetics of the magnetoelectric switching in chromia, first in bulk samples of chromia, and I think more recently in thin film samples of chromia. So this is an example of the work that came out around 2015, 2016. I mean, these people have been working, this is the Japanese group from Tohoku and Osaka who have been working in these samples for a number of years now. And what they did was they actually showed a reversal time of exchange bias in chromium oxide cobalt samples to be on the order of 100 nanosecond to a microsecond. And their measurements are done at 268 Kelvin. Now, this is important for us because we are trying to really understand these compact models, and I'll talk a little bit more about that. And having experiments which are really probing the reversal time is very important for us. And more recently, a qualitative estimate of about 10 nanosecond was provided by this group from Dresden. And this is purely qualitative. And both of these measurements were done in a chromia sample of 200 nanometer thickness. The use of thin film chromia is really desirable for scaling of devices and enabling future spintronics applications. And in that regard, a number of interesting results have been demonstrated very recently. So first, magnetoelectric induced switching of exchange bias has actually been demonstrated in films under 60 nanometer. So first, on the left side is a paper that was written by Professor Christian Binek and his group, where they demonstrated isothermal switching in 20 nanometer thick chromium oxide, palladium, cobalt, palladium samples. But unfortunately, the switching was not bidirectional. They did have bidirectional switching in thicker samples. And then in 2020, the same Tohoku/Osaka company, they actually demonstrated isothermal and bidirectional switching in 56 nanometer thick chromium oxide cobalt samples. And it was also concluded in this study that the thickness scaling was not adversely affecting magnetoelectric susceptibility in chromium, which is great for us because we want to be working with thin film devices. So that's exciting. So what was our role in this whole chromia-based memory devices and so on? And people have been working in this domain from the 1960s. So we were fairly new, and we were chartered to basically develop models for the magnetoelectric switching dynamics. What that means is, for a given amount of this external electric and magnetic field, material properties, setup parameters, how fast could this device switch? And then we also worked with Christian's group to explain boron-doped chromia switching mechanism. And finally, we also looked into SPICE models of the magnetoelectric RAM and its security implications, because if this is a non-volatile memory, surely we should be concerned about the data remaining in the memory after shutdown and things like that. All right, so since we're talking about domains, reversal, we have to think about domains. And domains in ferromagnets are formed because we have to reduce the magnetostatic energy, but that's really not the case in antiferromagnets because they do lack stray fields. But if you look at data, domains have been visualized in chromia using XMCD. This is an image from Professor Peter Dalbin's group. And experiments in the magnetoelectric reversal have also shown coercivity that is about 10 to 100 times lower than the magnetic anisotropy. And the switching time that I showed earlier, it's for the same sample, is on the order of 100 nanosecond to microsecond, which is very slow. So these results are strongly suggesting that the domain reversal is actually inhomogeneous in nature, and it's not coherent rotation. And indeed, in antiferromagnets, the local nucleation of the order below the Néel temperature and its subsequent growth could lead to the formation of the domain walls if the wall energy is offset by the gain in entropy. And importantly, if your sample contains defects, the domain walls could be pinned down by those defects, and then they would continue to owe their stability to the presence of these imperfections in the sample. All right, so now we have to think about all the different kinds of domain reversal mechanisms. So we looked into nucleation of reverse domains. That's the first mechanism that we considered. Here we consider a local droplet model. I'll explain this in a little bit more detail. The second process that we considered is this domain wall propagation. Here we consider both the thermal creep and the flow regimes of the propagation. And finally, if the size of this memory bit is small enough, hopefully we could also get coherent rotation. And if the exchange energy is much greater than anisotropy, then we expect that the sublattice moments would remain anti-parallel during the reversal mechanism. So what I want to do in the next 4 slides, I will give you a brief sketch of the theory and then apply this theory to the 3 different mechanisms and then show the validation of the model against experimental samples. So we're focusing both on the thermal activation and flow regime. So thermal activation means that the external magnetoelectric pressure that I've applied is lower than the coercive pressure for that specific mechanism. Here, alpha is that constant of proportionality that I showed you earlier. This is the magnetoelectric susceptibility. On the other hand, in the flow regime, this exceeds the coercive pressure. So thermal activation is basically an exponentially dependent process on the energy barrier that needs to be overcome in order to activate that mechanism. And then we have this pre-factor. So what we do for our models is that these pre-factors and energy barriers are modeled in terms of the specific physical process, as well as the material properties, which are temperature sensitive, and the setup properties. And then in the flow regime, we do not have any energy barrier. And so here, our dynamics is simply governed by viscous damping in the system. So for this case, we need to understand how fast the domain wall is moving, or in the case of coherent rotation, what would the damping of that precessional dynamics look like? So that's the general sort of like overview between these 2 systems. So this could, this part, the next 2 or 3 slides could get a little bit dense. So I'll try to simplify the situation for you. So here we are considering a cylindrical droplet model. This is a uniformly reversed order with a domain wall boundary in an otherwise single domain state. So in order for us to understand what we want to do in terms of modeling the dynamics, we have to first start with writing an expression for the free energy density. So here, the energy density would be the wall energy plus that external magnetoelectric energy due to that applied electric and magnetic fields that we need. And this is a thermally activated process. So here we need to compute the energy barrier for droplet expansion. We can do that by extremizing that free energy density term, which I'm not showing you with respect to this radius r. And what we find is that this energy barrier delta F is proportional to the square of this fancy E over here. And this fancy E is the domain wall energy. So we're already kind of taking the material properties and writing the value of delta F. And then in the denominator here, we have that external EH product, right? And so what this expression is telling me that I need to overcome this energy for this mechanism to take place. And so it's supporting the idea that nucleation is likely to occur at centers where the wall energy is locally reduced because of the presence of defects and dislocations in the sample. And we can combine this with the kinetic theory of domain walls and estimate the time scale of reversal. So we get this exponent, all is great. One thing I will mention, of course, it's telling me that if I applied a lot of magnetoelectric pressure, lots and lots of electric field, I'm going to make this process faster and faster. But there is a big problem in Chromium, which is that for a lot of, if you did apply a lot of electric field, you're going to ultimately break down the sample, which has been known to be a particular problem in thin film samples. In fact, for thin film samples, the breakdown actually reduces by a factor of 5 to 10 compared to the bulk value. So this could be a big problem in device scaling, and it is also a very active area of research. The second process that we're considering is this domain wall propagation. So we're considering that the wall is being intersected by the spherical non-magnetic inclusion. So we want to find the time scale. So it would depend on how fast this external electric field can move the wall to the edge of the inclusion, assuming that my magnetic field is something fixed. And again, we're going to formulate the free energy density, which would be the wall energy. But now we got to remove this kind of term that is proportional to the cross-sectional area of the inclusion, plus this extra energy coming from the magnetoelectric work that is done to move the wall. And then we have a deepening pressure, which means that this is the amount of pressure I need to apply from outside in order to move the wall to the edge of the inclusion. And like before, this is proportional to the wall energy, which is this fancy E. So again, if I didn't apply enough magnetoelectric pressure, I'm putting very small electric fields in my sample, the wall can still thermally creep to the edge of the inclusion. And for that particular case, we can formulate the energy barrier for that to happen. And we find that it is proportional to the domain wall energy. And we get an extra term, which depends on the ratio of F and FD. On the other hand, when we are in this flow regime, which means that I've applied enough electric field. And so now we need to understand how the domain wall velocity is changing with the applied ME pressure. And so more or less in the linear regime, it changes proportionally with the difference between F and FD. And this part actually has been computed very nicely in one of Kirill's 2015, I believe, an APL paper. I think I have a reference here. So anyway, we can write down the time scales for thermal creep, which is exponentially dependent on this energy barrier. And in the flow regime, what happens is the time scale is inversely related to the flow velocity. So what our job is to find ways in which we can maximize the domain wall mobility for a given magnetic field. And as I was telling about Kirill's previous APL paper 2016, where he did some calculations and showed that an in-plane strain could improve the flow velocity. So methods like that would be very critical over here. Before I go ahead, I want to mention that this model does contain a few free parameters. For example, I need to know the natural surface area of the wall, and I also need to know the mean free path of the wall. So one can estimate this from the distribution of defects in the sample, but what we do in our compact model is that we treat them as input parameters. So then the value of these parameters is extracted by calibrating the model against measurement data that we have. And finally, we come to coherent rotation. This is my third and last slide on all the different mechanisms. And after this, I'll show you some cool calibration results. So here we apply the Stoner-Wolfart model to write down the free energy, which then we extremize with respect to the orientation angle. And again, like before, if our magnetoelectric pressure is less than the anisotropy, we would be in the thermally activated regime. And here, very heuristically, what we do is we use the Neil Brown's theory of superparamagnetism to write down the time scale of reversal. On the other hand, for the flow regime, which is deterministic, I've applied a lot of magnetoelectric pressure greater than anisotropy. We would then be limited by the damping of gyromagnetic precessions. Now, the issue, of course, is, as I said, anisotropy is huge. You'll probably break down the sample before making this happen, and I'll show you some results for this in a minute. There are a few assumptions that go on in this, apart from the fact that this is a completely heuristic model. One is that we're assuming that our damping is angle invariant, as well as the fact that the energy barrier here is greater than the thermal energy. One could relax these assumptions using this jump noise formalism that we presented in 2018. And the other thing is that this is not valid for ultra-fast dynamics. So with this, I am ready to show you some very cool results of assessment of the model against experiments. So what we want to do is we want to take experimental samples. And if they have made measurements of switching time, we want to take our model and fit it to those measurements that have been performed. So I'm showing you two samples. The left sample is a typical sample that the Japanese group uses. This is an exchange bias sample. And the right-hand sample is from the Dresden group. This is also similar to some of the devices that Christian was talking about in his presentation. In fact, voltage controlled switching of the exchange bias was first actually demonstrated by Christian and his colleagues. And then the Japanese group has been very actively scaling down the size, thickness of chromium in order to demonstrate the switching of the exchange bias. Now, in the right-hand figure, they get rid of the ferromagnet and they attach platinum, and then they detect basically an anomalous. They actually called it an anomalous Hall signal. This is still a matter of debate. The main difference between the two samples is that this one is conducted at 268 Kelvin, and this one measurement is done at 292 Kelvin. And so what we do in our models before we start applying the models is we basically use the temperature specific properties of chromium. Now, I understand that these could be thin samples, but we don't have very good measurements for thin samples. So we are limited by the values of these material parameters that were measured in the bulk samples. But nonetheless, we have the uniaxial anisotropy, saturation, magnetization, and then these are the values of the magnetoelectric susceptibility for these temperatures. So now we can calibrate our model. So what we are looking over here is on the vertical axis, we have the time scale of reversal, and on the horizontal axis, we have the magnetoelectric pressure. So there are a number of traces over here. So I'll walk you through each one of this. The first one, the blue one, is nucleation. So what I'm seeing over here is that nucleation can be a fast process, but it is going to be activated at a very, very high magnetoelectric pressure difference if the sample was completely pure. And that's probably not going to happen because even at a generous magnetic field of about a Tesla, the breakdown strength is orders of magnitude below this 10 to the 6, 10 to the 7, 5 kind of numbers that we're getting here. Then, okay, so maybe I should also explain why two traces. The two traces are corresponding to the material parameters that we picked up from the two samples that I showed you earlier. Next, we have these orange traces, which are coherent rotation. And like nucleation, coherent rotation could be fast and it could be activated at modest energy cost, but it's probably not likely to occur in these devices. Yeah, and let me actually, yeah. Okay, and finally, we have these two red traces which correspond to the domain wall propagation. And what we see compared to rotation and nucleation is that this is extremely slow, but it basically has a very, very low energy cost. And in fact, the samples that we've analyzed, which are from the Dresden group and the Tohoku group, they're both limited by the domain wall propagation in terms of the time scale of reversal of the domain. So ideally, if I'm building a memory out of this, I would want this to operate at a faster time scale at lower energy cost. So what that would entail is either moving these yellow or orange traces to the left-hand side and or moving these red traces downward and then operating it there. And one of the ways to do that might be to scale the size of the bit. These were big samples. But the other thing, as I mentioned before, strain could be a very good knob to increase the domain wall velocity, at least by several times, in order to improve the time scale of reversal. And that combined with the scaling of the bit size might give us, I think Kirill predicted about 5 nanosecond for a 50 nanometer bit size in his 2016 paper. So those could be some interesting methods to look into. And then we also validated our model against this 2017 paper. This is also an exchange bias sample. But what is very exciting about this paper is that they actually do measurements of the switching time. So what they're doing here, they're applying a huge magnetic field. This is 60 kilohertz. So this is extremely huge, first of all. But what they do is they apply pulses of electric fields in the range of, I believe, 5 nanosecond all the way up to 10 microsecond for a number of different kinds of electric fields ranging from 200 to 800 kilovolt per centimeter. And then for each amplitude, they measure the exchange bias and the remnants ratio, and they define the switching time as the point where the remnants ratio goes to 0. And so we looked at this experiment and we applied our model of domain wall propagation, both in the thermal activation and the flow regimes. fixing the value of the magnetic field. And we compared the results of reversal time as a function of applied electric field. So these symbols are from the measurement data from that paper, and the solid line is the model. And we see that our model does a great job at determining the time scales, the trends are similar, so on and so forth. And then they measured a time scale that's less than 10 nanosecond for magnetoelectric pressure that is twice the coercive pressure. But we have to remember that the magnetic field is huge in this case. One might be able to reduce the time scale if we had a ferromagnetic free readout, perhaps. But in any case, so our model contains a number of fixed parameters, which are these unshaded rows over here. So these are material-specific parameters. We fix them during the model validation. We do contain a few free parameters that we basically extract by fitting the model to this measurement data. For example, the surface area of the wall and the coercive pressure, which is asymmetric. In exchange bias samples, it is known because of the effect of the interfaces that the coercive pressure would be asymmetric for positive to negative and negative to positive switching. All right. So far we've looked at pure chromium, and we developed models for magnetoelectric switching, and we calibrated the models of time of reversal as a function of the magnetoelectric pressure for different cases. But boron doping is very important because otherwise the Néel temperature is only 307 Kelvin. But through boron doping, we can increase the Néel temperature up to 400 Kelvin. This was basically theoretically first demonstrated theoretically demonstrated in 2019. This is huge work by Kirill again. And then we had demonstrations of it experimentally as well. I think this is a chart that, this is a graph that Christian also showed in his presentation. So when we were working with them, what we found was that boron doping actually creates new tunable functionalities in chromium. So for example, what they found in experiments was that the resistivity of the sample was increased, I think, by 2 orders of magnitude compared to the undoped sample, along with the enhancement of Néel temperature. But they also found that there was a significant spin canting relative to the surface normal. And they also found reduction in anisotropy, which probably would be detrimental for devices which are relying on a proximity with a ferromagnet connected to this antiferromagnet. But interestingly, they also found that the application of electric field created this transient polarization and piezoelectricity. And so essentially, after doing this boron doping, they thought that it was like a new multifunctional material platform, which is very exciting. And the unique thing about this platform was that they could switch the boundary magnetization only with the help of electric fields without applying any magnetic fields. So this is a cartoon of the fabricated device. This is a 200 nanometer thick sample. On the bottom gate is vanadium oxide, and then they have this Hall cross sitting on top, and they detect this transverse voltage in response to this in-plane current. And so here I'm showing you the hysteresis loops as a function of the gate voltage without the magnetic field and with the magnetic field. And what they find over here is that magnetic field has no impact on this voltage controlled transition, which is also very sharp, and it does resemble deterministic switching. The other thing that they kind of like found from this is that the hot voltage was switching between negative 15 millivolt to 0 millivolt, so which kind of is indicative of the fact that the Néel vector is rotating by pi by 2 rather than by pi. And it's okay because it is consistent with the fact that if it didn't apply the magnetic field and the time reversal symmetry is not broken, thus this is okay. So we had to work with Christian and figure out reasons for the switching mechanism, and hopefully also give them some estimate of how fast this switching could take place. I think this whole idea of figuring out time scales and energy dissipation is very critical, especially this was an SRC project. So they really wanted to know if this would be a competitive, viable platform to realize next generation Spintronics memories. So anyway, piezo-force microscopy data was collected, which did show induced polarization. And we're looking at this butterfly-shaped amplitude curve. And this is asymmetric. And this was attributed to the residual strain near the surface. And the reason that we think for this polarization is the polar nanoregions. They are formed because of the random substitution of oxygen atoms by boron atoms, and there's a local inhomogeneous strain. So when we're applying this electric field, it acts to reorient the PNRs, resulting in this piezo response. But once the electric field is removed, then we see that the piezo response decays logarithmically in time. Right, so this is a transient effect, and also this is similar to magnetic viscosity effects that have been reported previously. But anyway, we get this global strain, and due to the application of the electric field, which couples to this perpendicular anisotropy through magnetoelastic coupling, leading to this Neal vector rotation. And this part, this fourth bullet point here, this is again another theoretical work coming out of Kirill's group, which showed the modification of the perpendicular anisotropy through strain. And we basically used a Landau-Lifshitz-Gilbert model in order to estimate the switching speed. And we found it to be around 100 picosecond. And again, we have to take this with a pinch of salt, because currently measurements of dynamics are extremely lacking in the literature for this material platform. So with that, I will move to part B of my talk on SPICE circuit modeling. And I have to say that this is something that it's very critical, because we have to take the models and then give them to circuit designers so that they can work with them. So what we did was we implemented this resistor capacitor network representing the domain wall propagation. We implemented this in a 15 nanometer CMOS technology. And here we said that the input to this magnetoelectric component is coming from the bit line. This is this current source. And then we represent the boundary magnetization using this voltage node. Apart from this magnetoelectric component, we also have peripheral and sensing circuitry. So we have this voltage controlled voltage source, which transduces this boundary magnetization into a voltage signal, which then sends it to the sense amplifier, and the sense amplifier converts it into a rail-to-rail swing. What we found when we were doing this is that these signals, I don't know if maybe it's spin Hall magnetoresistance combined with anomalous Hall effect, but whatever, we're getting some Hall signal here. They're very small, and in the previous one I showed you 15 millivolt of Hall signal. So what that means is that from a CMOS design perspective, my sense amplifier design gets a little complicated. So that is something that we have to remember when we are designing these memory cells, that getting better transduction efficiency is very critical in order to enable CMOS integration and so on. So we also looked into the array level analysis using this tool called NVSIM, which is basically a standard evaluation tool for emerging memories. And I'm not showing you what goes on in the tool, but what it does is it allows us to benchmark arrays like 64 kilobyte memory arrays against existing memory technologies. And what we find in this table at the bottom is that the magnetoelectric memory has competitive metrics compared to the other memory systems. And on the read side, most of the latency, we're seeing 2 nanosecond, that's due to the sense amplifier delay. And on the right side, we do have the domain wall propagation. So that's kind of limiting, even though we scale the size of the bit, so on and so forth. So, but it's still competitive, and hopefully, if we did a little bit more device and material engineering, probably we could improve this. And I haven't yet implemented models for boron doped chromia. So yeah, so this is just for undoped samples. Anyway, so memory security. Why am I talking about memory security? So there has been a lot of work going on in security, because these are non-volatile memories. So there is data remnants, and that poses a threat to data confidentiality, because someone could come and just launch a cold boot attack or steal your memory module. And so people have been working on these encryption schemes, and one of them is this counter mode encryption. So I know perhaps this audience isn't familiar with, or even I wasn't familiar with when I started working in, looking into security. So this block diagram probably helps in that regard, because the way that this encryption works is what we are wanting to do here is wanting to convert this plain text into a cipher text before storing it into this non-volatile memory. So we have a core which is going to basically generate a one-time pad and we have a secret key, we have a line address, and we have a counter. And then this one-time pad becomes unique for each line address and each write. And then what we do with this OTP is that we XOR it with the plain text to create the non-volatile, to create ciphertext and store it into this non-volatile memory. And throughout this, it's assumed that this key is inaccessible to the attacker, which is fine. But one of the biggest issues with this CME kind of scheme is that it's basically targeted towards slow memory systems because it encounters encryption overheads. So in order to alleviate that, we basically came up with our own encryption scheme called InMemory Encryption. And also this was a good sandbox for us to test our SPICE models in the context of a new sort of application. So the main difference between what has been done before and our case is that we remove the XOR gates and implement them with these bitwise CNOT gates. And these CNOT gates are controlled NOT, so they can act as a buffer or inverter depending on the control signal. And I think one might be able to implement them with Peter Daubin's transistors that he proposed in 2018. So we haven't looked into that very carefully, but I think we could do it that way. So here is the architecture that we implemented. So everything is, again, synthesized in cadence. So those SPICE models are very helpful. So here again, we have this key processor in a secure processing module. And then we are basically putting everything in AES, and that's creating our encryption pulse. And we put them into the CNOT gate, and then we encrypt the data and write it. So we said, okay, great, this works. Let's benchmark, let's compare with the CME scheme, the counter mode encryption, and our scheme. And sadly, we thought like we would get a lot more benefit with in-memory encryption, but our benefit was only 20 picosecond, as you can see over here. And also the energy numbers weren't that impressive, but I don't want to get into the details of this, but I think the reason energy is not very good here is because the energy is anyway dominated by the AES core. So that's something that we cannot do anything about. Anyway, so we have a new book coming up with my ex-graduate student, Nikhil, on this next era in hardware security. And we talk a lot about how to take these emerging devices in physics and create some sort of like polymorphic or reconfigurable logic devices, which might provide us more immunity on the chip. And I think the semiconductor industry is now realizing that security should be a very important aspect of the design cycle. And there is this upcoming webinar on measurable ICT security and privacy next week. So this is something that I think as an ECE person, where we can work with material scientists as well as work with circuit designers, is very helpful for our group. All right, so I know I'm probably almost to the end. So if the organizers want to stop me, let me know, or should I continue talking?
You can keep going, it's fine.
Okay, perfect. Okay, so this is the last part, and I know that I was asked to speak for 45 minutes, but if history is any indication, that never ever happens with me. So anyway, so I'll take the next 10 minutes to go over our active device, which is the spin torque driven device. So we're moving away from the magnetoelectric memory and so on. So we're going to work with these collinear bipartite antiferromagnets, which have these oppositely aligned sublattice moments. And in the limit of strong exchange, the Neal vector, which is the difference of the sublattice moments, is approximately equal to 1. And if we do apply a spin current, it does create a dynamic instability in the sublattice moments. And we can get these precessions in a plane that is perpendicular to the spin polarization at terahertz frequencies. And terahertz frequencies or terahertz sources are very useful for imaging, sensing, and in fact, work that's coming out of this group, Professor Slavin's group, who have been doing this for the last 5 years in antiferromagnets. They've shown that it can also be used for neuromorphic computing. The biggest benefit here is that this is operational at room temperature, and it's in a compact form factor. So why were we doing this, even though a lot of work has already been done and it's still ongoing from these big groups like Professor Slavin's group? So I think what we wanted to do was to basically have a more systematic understanding of this equation of motion of the order parameter, and importantly, develop analytic solutions, compact models, so that one could use those models and also work with materials and see how to do this material device kind of optimization, and also work with circuit designers and see what kind of devices and circuits might be suitable for signal detection in this particular case. So again, I promise I'll be very, very brief with our sketch of the theory, but I think it's difficult if I don't present this and then just show you the results. So we're working with these biaxial antiferromagnets. So there's an easy anisotropy, there's a hard anisotropy, and there is an exchange. And we work in the spherical coordinate system where we are measuring this polar angle theta from the direction of the spin polarization. And when this spin polarization is along the hard axis, then we get theta equal to pi by 2 as the stable solution. And by doing some angle transformation, we come up with this second order differential equation that describes the evolution of the Néel order on this unit sphere state space. So this equation is similar to the equation of motion of a simple gravity pendulum with mass, length, and gravity equal to 1. This was already recognized in the previous paper reference that I showed you on the last slide. And this is a gravity pendulum that is in a damping of beta, and that is driven by the star gamma. So in the context of antiferromagnets, beta represents dimensionless damping. Gamma is the spin current that I'm putting in order to get these oscillations. But the nice thing, so this is where our work kind of deviates and diverges from the work that other people have been doing. We are really trying to find out analytic solutions of the transient solution for phi prime over here, because that's the angular velocity. And there are some works already that talk about this phi prime in terms of in the limits of small and large damping, but a general solution was lacking, which is what we provided. We also looked into some new kinds of detection schemes which could employ hysteresis in this equation. This has inertia, and it does show hysteresis, and so could we exploit that in order to come up with a more energy efficient oscillator? So that's what we've been doing. And so we analyzed this equation in the 2D parameter space of beta and gamma. Remember, beta is this damping of the antiferromagnet. This is a property that is fixed for the antiferromagnet. There will be some contribution from spin pumping and so on. Thin films would also be different. And then gamma is the spin current drive. So here we're looking at the heat map of the steady state frequency. To obtain this heat map, what we do is we run time domain simulations. We can do that very nicely for a number of beta and gamma values. And then what we obtain, what we find is we find the time it takes for the Néel order to complete one revolution in steady state at long time. And that's how we obtain this. We start with an inverted pendulum, right? And we do this. And so we can see that there are periodic and stationary solutions. And in the periodic case, you're getting nice periodic phi prime. And then if your spin current drive is large, you have to remember this drive is large, I'm getting this nice coherent oscillations. And then if my damping is large and I'm close to this dashed blue line, I get this spiky behavior. And this is why I think Slavin's group was calling it, I think, a hardware emulator of a neuron or something. I'm not from neuromorphic, but I think that's the general sort of idea here. And then we also have the hysteretic region where we can get periodic or stationary solutions depending on the initial condition. And this is what we can kind of like exploit for working with these oscillators. So in all of these four kind of like plots on the side, I'm showing you two traces. One of them, the solid one, is the actual numerical solution, and this dashed one is the analytic solution. So that's where I said we diverged from previous works. We came up with these analytic solutions and so on. We also did a little bit more, and let me talk about the solution space a little bit more. So we have these, let me talk. So we have this dashed line. This is the minimum current that is needed to start the oscillations. And if we applied a lot of spin current, then we can find out the fundamental frequency of oscillation, which scales with the spin current and the damping of the system. What is this gamma M over here? The gamma M is this bifurcation line. So it's separating these regions. And this is the minimum gamma that is needed in order to sustain the oscillations. What we find from our modeling is that this is a cubic function of beta. And so one can actually reduce the current by 1 by beta and sustain these oscillations in the hysteretic region. And in the overdamping region, we also have an equation for the frequency. And these actually merge with each other if we have gamma significantly greater than 1. But let's not get into that. It's important to think of geometry. So one can think of using a spin Hall structure, AFM coupled to a material like platinum, where we can pass a charge current, create a perpendicular spin polarization, start these oscillations, and get the spin pumping signal back and measure the output. Of course, this hasn't been done. So, but that's the general idea. And for a given amount of spin current, one can also estimate this is the charge current that I would need in order to start these oscillations. And that would require understanding of the interfaces, property of the non-magnetic layer that I have here. But what our analysis shows is that we can get threshold currents around 10 to the 8 ampere per centimeter square in a frequency scale of half a terahertz and a few microvolts signal at the threshold for properties that are specific to Chromium. We don't really know the interface properties that well, so we're using some sort of typical values for other materials. So let me put it that way, and it would be good to have some experimental demonstrations here. This is our most recent work in emergence of chaos, and we were also looking into solutions that are just beyond periodic solutions. So we actually here we considered a uniaxial antiferromagnet, and we consider that it's starting from an unstable point, and our spin polarization is at a certain angle. And again, we work in this spherical coordinate system. So we are looking at theta and phi, polar angle and azimuthal angle. So if we can come up with this equation of motion, it can tell us how the Néel order is kind of evolving on this state space. And we do exactly that. And remember, gamma is the current I'm putting in to start this, and beta is the damping. So this actually is a very, very interesting system because it has a nonlinear structure in 4-dimensional phase space of theta phi, theta prime, and phi prime. Someone that's more mathematically competent than I am should be able to work with this system and look into, fractal patterns and things like that. And I think there's a recent paper that has just come out that cites our work in chaos. But what we did was we looked at it by simulating it. So we fixed the damping and we said, okay, let's have a very small amount of current, and we get these stationary solutions of the Néel order. We put more current, gamma equal to 0.6, we get nice periodic solutions. And it is in between these two regimes where we get chaotic solutions, which is aperiodic in the long run. We get this dense topological mixing. And again, I think I think there could be some use of this. I just don't know where one might use these nanoscale chaotic elements. So that's our most recent work, and we're hoping to kind of like get a little bit more insight into this. Okay. All right, so I do want to close my talk. This is my last slide. 3 future research directions for students who are looking to work in this. And I think this is very important. First, thin film properties are very critical to know. We still don't have a good understanding of how Chromium behaves in its thin film form, the breakdown fields, how can we improve them, how can we dope it with boron, so on and so forth. And also, we don't have a good understanding of how the material properties are distinct from the bulk. Second, very, very important is understanding of the dynamics, which is lacking. And finally, I think Professor Axel Hoffman said this very succinctly, and I couldn't have said it better, which is that a clear experimental demonstration of electrically driven coherent magnetization dynamics in antiferromagnets is the next milestone. And it has not been demonstrated yet. So that is something to also kind of think about. And that would give us a validation of some of the things that we've been doing in our group. And finally, I want to acknowledge my students, Arun and Nikhil, who did majority of the work reported here. I want to thank Christian and Peter at UNL for kind of absorbing me in their group and teaching me a lot about Chromium. Of course, I don't have as much experience as they have, but it was really great working with them. and Professor Kent at NYU, and Professor Sinanoglu at Abu Dhabi, who is an expert in security. So I learned something from him during this process. Finally, I have to say that I have several PhD positions open in my group. So if you have students, please send them to me. With that, I sincerely apologize for taking significantly more time than I was allocated.
Thank you very much, Shaloo, for this very interesting talk. Let's thank her by using the reactions buttons. So we're open for questions. Please use the raise hand feature in Zoom, or if you're in Twitch, you can type in your question. Let me make sure I have that window open. So the first question, Alexei, please go ahead.
Hi, can you hear me?
Yes.
Thank you for a nice talk. So I have a question about domain wall dynamics. So we would like to switch perhaps some memory very fast. So we want the domain wall to move as fast as possible. And in an antiferromagnet, it is known that relativistic physics can play a role. So how important do you think it is, for example, Lorentz contraction and stuff like that, and if it should be taken into account in chromium oxide?
Yeah, so our model of domain wall propagation is a very simple model that actually was presented by Kirill's group in 2016. So I would basically defer to his expertise in that regard. But what we have found is that if hopefully we could apply strain, and that might help us improve the domain wall velocity. And remember, some of the devices that we're looking into are extremely kind of large, at least from an experimental standpoint. So we also don't know once you start scaling how things would appear. But for this simple case, we've not considered a lot of the fine details that would be coming from the physics. Our goal was to develop a compact model so that it could be calibrated with experiments in a relatively straightforward manner. And one could actually introduce more complicated physics, hopefully by kind of, again, it depends on the kind of complexity that you have and whether or not you can fit it to experimental data. Since we have been able to fit it with experimental data, I think it establishes it's a fine balance between first principles calculations and sort of like a completely heuristic model. So I think for now, we're okay. Hopefully in the future, we can make it better.
Okay, thank you.
Okay, thank you. I think if you're getting into that problem, I think you're already doing pretty good, because that means your domain wall velocities are approaching the limit, right?
For our case, if I may mention one thing, the samples that I showed you, the domain wall mobility is 2 orders of magnitude lower than theoretically predicted. 2 orders of magnitude.
Yeah, but potentially we would like to switch as fast as possible. So
there's a long way to go, I suppose.
That's from a compact modeling. We're trying to match with experiments. So we want to extract what these mobilities are, and we find that they are just like extremely, extremely bad at this point. So hopefully people can do better than that.
Okay, yep. Okay.
Okay, thank you. Further questions, please? Please use the raise hand feature if you have a question. Chen, go ahead, please.
Thank you very much for this very interesting talk. I actually have 2 quick questions. On slide 23, you simulated the write latency. That's still based on the domain wall motion model, right? It's just the device is small enough, so the switching takes shorter time. How small is that? And are you able to actually move to a single domain region that it just becomes completely coherent switching?
No. Second question, we are not consider. Again, I will go back to this model first. So we implemented the model specifically for functionally representing domain wall propagation. So this is not accurate in terms of how the domain wall is moving, but it's accurate in terms of the time scales. So we're not looking into a coherent rotation model. One might be able to do that by putting, I suppose, two equivalent circuit models for magnets that are coupled through some exchange. And I think some work has already been done at Purdue in their, I guess, like spin equivalent circuit models or something like that they've been doing on NanoHub. But we have not done that. We still consider that it's a small cell, so we get faster dynamics, but it's still limited by domain wall.
I see. The second very quick question is when you describe the magnetic, the part of the encryption, you used an example that to prevent a code booting. But how can encryption help with a code boot?
Yeah, so basically in cold boot, what people try to do is during the time that the memory is turning off and it's fully turned off, data can be stolen from that. Encryption can, even if they launch a cold boot attack, the data is already encrypted. So that's the benefit of encrypting. The problem with what I have presented is that we cannot prevent side channel attacks, because we talked about this, that switching is not symmetric. So it's happening at different voltages, positive to negative, negative to positive. But cold boot, that data is already encrypted. So that is okay. But the side channel attack, that would be a big problem.
I see. Thank you.
Okay, Alexander, please go ahead with your question.
Do you hear me?
Yes.
Yeah, thank you very much for your talk. I have a small question to the model of the domain wall you shown in the first part. There was anisotropy in this model, but I missed exchange stiffness. Do you need it here?
Yes. Yeah, so basically what we're doing is we're modeling things in terms of, so maybe I should go to the flow velocity model, maybe that I can show you specifically. Yeah, correct. Can you see? Yeah, so correct. So basically the domain wall velocity is modeled in terms of the material parameters as well as the external electric and magnetic fields. So over here, we do take into account the damping, the domain wall width, which in turn would depend on the anisotropy. The energy of the wall would in turn depend on the anisotropy and the domain wall width and so on.
Mm-hmm.
So the model does include that.
Okay, thank you.
Mm-hmm.
Okay, thank you.
And maybe this is also something very interesting I could point out, because this is what we were talking about the domain wall mobility. So here you can see that the maximum is limited by this mobility, and then you have the domain wall properties, the width of the domain wall, which does depend on the stiffness and the anisotropy. So I've plotted it as a function of the magnetic field that you would apply, and maybe you get between 10 to 100 meters per second for 100 to 1,000 Ørsted of field. The problem is in experiments, they got a 5 meter per second speed, but they got it for 60 kilo Ørsted, which is like 3 orders or 4 orders of magnitude more. So their mobilities are extremely terrible. But anyway, the model does contain the relevant parameters of the material.
Yeah. Let me ask you, you mentioned that in some experiments or in some samples, the switching can only occur in one direction. Right?
Oh,
you
I didn't look at those. Oh, right. Those are correct.
That it's not bidirectional. So why is that? Is that because you can expel the domain walls, but then you cannot nucleate them back, or is there something else?
Yeah, so this is actually Christian's work, where they were only able to switch it in one direction at 20 nanometer, I suppose. And when they increased the thickness, they were able to switch bidirectionally. I'm guessing that the problem has to do with exceedingly high contribution coming from the interface. And that's probably one of the challenges. But then they started relaxing in the same paper from 20 nanometer to about 250 nanometer. And I think the sample that Christian showed in his slides last week is from the same paper, but a thicker sample where bidirectional switching is noted.
But I mean, do you think that it's the nucleation problem? That they cannot nucleate the reverse domains when they try switching back?
Yeah, I would guess so. I would guess so.
Okay. And the other thing I wanted to ask, so when you showed the estimate of the critical nucleus, you use the model that it's cylindrical, so that assumes that it goes through the thickness of the film. So at some point, it should become three-dimensional when you increase the thickness of the film. So where is that crossover?
Correct. So that's a phenomenological model. So we just treat it as a fitting parameter for the model, and then we extract it by calibrating the model. And currently, we are doing it this way because of the limited amount of experimental data that is available to us. But there are some other works that are looking into dimensionality related effects and things like that. But that was outside the scope of our kind of investigation, where we wanted to focus on specific experimental samples where the model could be calibrated. So yeah.
But qualitatively, at which thickness of the film would your nucleation start to be three-dimensional? Is it just the domain wall width, or is it something else?
Yeah, so that's actually a very good question. So we've looked into different kinds of samples with different thicknesses, and I think domain wall thickness is a good example, but it could be few domain walls. It's very difficult for me to say, because I suppose, let me just go here. We're talking about this, right?
Yes. Yeah.
Yeah. So again, as I said over here, so what we're doing over here is something very, very simple. We're considering that, okay, let's just write down the free energy of the system and then just extremize it. So obviously, it's based off of a very, very simple model. And over here, if you look at this sort of this energy barrier, you do get kind of like this sort of a relationship. But I really don't know. I mean, you're talking about this thickness D, right? Mm-hmm. Yeah, I mean, the samples that we have currently are 200, 300 nanometer. Where this starts to transition is your question, if I'm understanding this correctly.
Right, into something that looks more like a sphere.
Correct. Yeah, I wouldn't be able to say, because D is basically, it's a free parameter. I just kind of like use this based off of the experiments that we're looking, which are in several hundreds of nanometer thicknesses. Mm-hmm. Yeah.
Okay. I'm just wondering that, I mean, if you look at this expression, so you get this delta F that is diverging when your magnetoelectric pressure becomes small. So that cannot be a parameter if that pressure is small, but you can have some thermal nucleation of the domains. And in a ferromagnet, they nucleate by themselves thanks to magnetostatics, but they can also nucleate in an antiferromagnet just through thermal fluctuations, even in the absence of any driving force. So do you have some intuition of what to expect in that case?
Yeah, so you're right that our model is actually diverging. In fact, all the models are kind of like, you can see over here, right? Like it's basically very, very, again, I have to say this, that, the problem of nucleation of domains in antiferromagnets, I don't know, like it's a difficult sort of a thing for me to say. We assume that there is this nucleation center that's present, and let's try to move it. And let's try to see if this will expand or not. And so if there is already a presence of defect, or maybe the dislocations are present, maybe they could lower the wall energy, and maybe this nucleation center would exist. But if you're asking in a pure sample, I don't think, like, how would you nucleate, how would you cause this nucleation in an extremely pure chromia sample? What do you think about it?
Well, I mean, there should be some thermal nucleation rate. You can have a reverse domain nucleus. It costs some energy, so it should occur in the Gibbs ensemble with some rates.
Correct, but if you look at it this way, that if it's a completely pure sample, then the formation of the wall is going to cost you a lot more energy. So it wouldn't happen. So it would happen at places where there are pre-existing defects or dislocations in the sample, correct? And so that's where we start with. We assume that there is some critical radius. So we find that critical radius. I'm not saying that we don't find that critical radius. And that critical radius, so if the radius is smaller than that, then the wall would kind of like, this droplet would kind of collapse. And there has to be some finite critical value of this radius in order for this nucleation to happen. How the critical radius is created, where it is coming from, what's the physics of it, that I really don't know. But you're right that we do consider that there's a minimum radius that is needed, and then you move it and then you expand it.
Okay, thank you very much. I think we are out of questions. So this is the last call. If you have a question, please raise your hand right now. If not, let's thank Dr. Rakheja again.